All right, welcome everybody to week 17, day 2. Today we're actually going to be learning some computer science. Background is, of course, Subnautica, one of my favorite games. I played the sequel. The sequel was good, but not as good as the original game, I have to say. Added some extra options for building, but like the story was just not as good. The original game was just an absolute masterpiece of game design. Okay, so upcoming things, we're going to have an ACM talk, extra credit talk on campus on game development on Friday at, I think it's like 5 or 6 o'clock. Stay tuned for the announcement on that on Canvas. We're going to be learning Unreal Engine and things like that. And yeah, we're actually going to learn computer science today because I kept threatening to have a lecture on Const, and I never did. So we need to learn about Const today. So const is a keyword in C++. You might have seen it doing something like this: const int points per touchdown equals 7. And this is, a pretty common use for const, or you might have seen it with a const reference parameter. The const keyword, though, in C++ has about 7 different uses. And we're going to go over like some of them today, not all of them. They appear in different places. All of them have, generally speaking, the same meaning. So, learning point number 1, const means the value can't change after it is set, basically. It's read only after it's been set. Okay. So, if I tried changing points per TD to be 12 here, it won't compile. You guys understand? This part's pretty straightforward, I think. The computer science is 10% computer, 90% science. 50% computer, 50% science, 50% debugging errors. Yeah. Off by 1 error. So, yeah, can't do it. Okay. So, the reason why we use these constants is we want to avoid learning point number 2, avoid magic numbers. And I can do a whole rant on these things, but I'll just kind of give you a short example. Let's say you're making a football game, real football, not soccer. And the World Cup going on right now. I had students like watching soccer while I was lecturing today. So let's say I'm making like Madden or something like that. EA bought the rights to all NFL players' faces. So even if you're an NFL programmer, you can't put your own face into a game because you don't own yourself. The NFL does. They own your likeness, and EA owns that. So the real football. So let's say you're doing this, and somewhere within your code, you've got like some score or something like that, and team 1 score 0, and team 2 score equals 0. Let's say you're like a million lines of code in, and somewhere someone scores a touchdown. Now, if you could say this, you could say team 1 score plus equals 6, right? Did I say 7? It is actually 6 points per touchdown, not 7. So you can add 6 to their score. Now, that's cool. You'd probably pass the test cases, right? You score a touchdown, the point goes up by 6. Good on you. And then somewhere else, there might be some code, a million lines of code later, and inside of there, you might have team 2 score plus equals 6. Cool. Now let's say the NFL changes their rules, and a touchdown is now worth 10 points. Or 5 points. Maybe 5 points would be interesting. Then field goals would be worth more. Let's make it 7. Let's make it 7. Okay. My subconscious type 7 because there's always the extra point, right? So we're gonna change this to be 7 points. Now here's the kicker, right? These giant spaces here represent millions of lines of code in between them, and you like hunt around and you like find the place where somebody put a 6, and you like search for 6. You're like, aha, that needs to be a 7, right? But then you forget to change this one. Then every time team 1 scores, they get the new point total of 7. Every time team 2 scores, they get the old point total of 6, and your code is very buggy. And so anytime, here's a general rule of thumb, avoid magic numbers. Anytime you have a number just sitting there in your code like this, don't. don't have that. This is bad coding practice, okay? The only numbers that like I would allow are like these things, like, you know, initializing something to 0, right? Or like, you know, the I++ is part of a for loop. Adding 1 to a number, everybody understands. Initializing something to 0, everybody understands. You don't need to explain it. But if you ever have something like this, then you need to use a constant instead. So points for TD and points for TD. So if the NFL ever changes the number of points per touchdown from 6 to 7, you only need to change it here, okay, in one place. And then every part of your source code, if you've done your coding properly and used the constant, everywhere within your code will update and have the correct change. And this is really important because a lot of students don't understand, because every week we work on a new project. We do Bank a Key this week, we do Pokemon that week. In real life, you don't just start a new project every week. It's very unusual. Like the way that we teach computer science doesn't reflect reality, because we give you a new project every week. In real life, you work on the same project for 10 years. You know, like you don't just like, all right, well, that's done. That's out the door. You know, let's do a new one. And maybe, I mean, if you're doing consulting, like you'll move from company to company that you're working with. But the thing is, like, you know, the reason why we have these different homework assignments is so that you can learn the different concepts, right? Like the data science was there to teach you how to like parse files and load files, and Pokemon was there to kind of teach you about classes and maps. And you know, like each one of these different assignments is there to teach you a different skill. But in reality, code maintenance is what you spend far more time doing, like updating your code and fixing your code and adding features to your code. You spend far more time doing that than you do writing like a brand new project every 2 weeks. Now, maybe there's some people that do, you know, like consultants. You know, if you write these like little programs, maybe as part of like, you know, your business workflow, maybe you're working on new stuff every week. But most, you know, software jobs, like your company's got a product and you got to learn the product and you got to know how it works. And a big part of your time is going to be maintaining the code base. You know, Congress passes a law making daylight savings permanent. You're like, great. Like for anyone who's ever worked professionally as a programmer, you know just how big a pain time zones are. Localization issues, like handling different, like in Europe they use commas instead of decimals and decimals instead of commas and numbers. Just being able to handle like different phone numbers and different time zones, like that is like the biggest hassle like ever. Like you think in college, you're like, oh, I'm going to be doing Dijkstra's and all these like hardcore algorithms. No, the pain in the real pain for most real programmers is just like, oh, the US has just changed the time zones again. And then, you know, there's just a collective like round of crying from the industry, you know, when a state decides I'm, you know, Arizona time, like we're going to be like California part of the time. We're going to be like the mountain states part of the time. And then people go like, consulting best time. I've been on this one project for almost a year now, although reading their legacy code has been exciting. Yeah. So this is a trick you can do, and it's not a trick, it's something you should do that makes it easy to maintain your code. There, now every touchdown's 70 points. Boom. That's what you should be doing. Do not use magic numbers. Okay. So that is the basic meaning of const, is that it's set, it can't be changed. Now, what if I did this? Does this work? See, what we had before was something that could be known at compile time, right? The compiler can know what the value of points per TD is. And so down here, the code that was probably generated just a second ago would have been team score plus equals 7, right? Or 7 or 6, whatever I had it at before. Now, it's being read from the keyboard. So we have a constant that reads, what? Huh? Is that really a constant? Is it a variable? What is it? Like, how can you have a constant that changes every time you run it? And Atari Simulator, yeah. So, yes, this code actually does work. And that's one of the reasons why my read library is the superior product. You can't do this with the standard library at all. Type in 90, and then points per DD is now 90. Okay. So yes, a constant can only be set once. The value of a const is set one time only. Okay. So it can actually be, it doesn't have to be hard-coded into your game, or if this is a game, right? You could load the value of points per TD from a file, and this would be fine. And so you could have like a config file that says, like, in Europe, touchdowns are worth 4 points, because everything is smaller in Europe. I don't know. So so you could actually load this from disk and then set the constant, and then the constant can't change after that. Okay. So it's European football now. All right. So that's the basic meaning of const. Now, then you already know const reference, right? I've hammered this into you guys enough times. Int accum, int vector. What do I want to do here? Let's do it. So we will get passed in a vector by const reference, and we will add up all the elements in the vector and then return it. Okay. So why do we make this const? All right. I could have a vector here. I could have vector events named vec is equal to 1, 2, 3, 4, and I could cout assume vec. And what is this going to print to the screen? Write it on Discord. Seeing if you're paying attention. So I'm very uncertain the answer is 10. So we've got a vector here whose elements are 1, 2, 3, 4. And then we've got this code here that says for every element in the vector, add that number to the sum. Sum starts at 0, returns the sum. So yeah, the sum of the numbers from 1 to 4 is 10. So if we run this code, it's 10. Will the code run properly? Will it run if I take the const out? Will the answer change? What do you think? Am I still going to pass my test cases if I make it not const? Remember the rule of thumb, right? The rule of thumb is const reference by default, not always, but by default, anything not a primitive, right? Not an int. So you already know that. That's why it's not a learning point for today. But, that's one of the uses for const, right? So yeah, it'll still pass. Yeah, it'll still compile. It'll still pass the test cases. It'll take the same running time. It's fine. And the reason why it's fine is because const doesn't change any of the actual execution of the code here. What it's doing, it's preventing me from accidentally shooting myself in the foot. If I did something like this, which a lot of students did on Rainfall, they did a sort from vector.begin to vector.end, right? And then they would print the first 5 values of it. So why will this code not compile? Why can I not sort vec? Why am I getting a little, compiler error here? This code is correct, right? We got algorithm included, we got vector. Why can I not sort a constant vector? Yeah, because sort modifies the vector. Exactly. And so the const here stops us from blowing our own foot off by foot gunning ourselves, like Keith. Okay? So that's why we do const reference. The const parameters stop us from accidentally modifying vec, back, and main. right? It would be very odd. Like if you're in main and you say, hey, add up all the things in this vector and it sorts it for you, you'd be like, wait, what? What? Huh? You know, you'd be very upset. Or even worse, if it like erased elements out of it or something like that. Dude, I just wanted you to add it up. I didn't want you to like sort it. I didn't want you to change it. And so having a const here prevents that sort of accidental behavior. Now, if you wanted to sort it for whatever reason, like you wanted the top 5 or whatever, you could always do this. You could say auto vec2 equals vec and just copy it into a new one, which is not super efficient, but like, there you go. And then you can sort this, the clone of it, right? So you just duplicate it and then sort the duplicate if you want to get the top 5 days of rainfall or something like that. That works fine. Yep. But by default, yeah, const reference is the way to go. So that's what the const means there. The const here means you can't change the parameter. Now, you could do a const by value like this. You'd say constant x, but nobody cares. Nobody cares because the when you do call by value, it's a duplicate anyway. And if you change the duplicate, like who cares? You know, like you could do that. Or actually, I already have an x here. Constant y, and then if you said like y is equal to 42, like okay, sure, yeah, that doesn't work, but it's very rare to have like a constant call by reference parameter because let's do this. So y is like this. Okay, so we're taking in a initial value, and you're like, don't change the initial value, and it's like, okay, I mean, you can do that, and you know, if somebody tried doing, you know, initial value plus or something, like, okay, sure, yeah, that doesn't work. I mean, it's fine. It's just it's very rare for people to care, right? Because if you change initial value, it doesn't change the value back here. Whereas if you accidentally sorted vec, this would get sorted because it's called by reference. Called by value parameters, people don't care that much about. But yeah, you can make it constant if you want. And then, and part of the reason for that is because some students don't know the difference between, like, I've seen this code written in this class. All right. And so, like, they don't know the difference between, like, plus initial value and, like, initial value +1. Okay. And you're like, well, what's the difference? You know, I don't see the difference. You know, does anyone know the difference between these two lines? Let me make it not const, right? Because the const is stopping us from doing this. Right? And intial, intial, initial. There we go. Intial. Thanks, autocomplete. Yeah. All right, there. So what is the difference between plus initial value and initial value +1? What, like, some students think they're just interchangeable, and they're not. These are quite different things. The top one increments before, the other after. This one actually doesn't increment initial value, right? It adds 1 to initial value, but it doesn't actually increment it. And initial value doesn't change in this case. This one adds 1 to initial value, and this and saves it into initial value. This one adds 1 to initial value and does nothing with it. Right? That's why you're seeing a warning here, right? The warning is because we're not doing anything with it. And so C++, the compiler, is like, it's cool that you're adding, you know, 2 numbers together, but what's the point? It's not doing anything. So did you mean to, like, save that or something? Like, why are you, like, you know, like, this is valid C++. Right? Do you guys see that? Like, there you go, 420 dudes, you know. That's perfectly acceptable C++. If we compile this code, it will compile just fine. We'll get a warning on it. Like, warning, it doesn't do anything. Like, okay. Okay, 420. Okay. it doesn't do anything. Like, it's completely pointless, right? You can do it, right? So yeah, you would have to say initial value equals initial value plus 1. Now these are equivalent statements. But a lot of students think that these two things are the same, right? Because this one doesn't actually change the value of the variable, right? And so if you made this a constant, then it would catch this one where you, like, maybe you're trying to add 1 to a number, but you don't know the difference between adding 1 to. It's like I've seen students just use plus plus where they meant to do this. And so if you make it a const, it'll catch that error. It's not something I really worry about because I know enough computer science to not make that mistake. But the point is, like, you could put a const there if you want, if it shouldn't change. Anytime a variable shouldn't change, make it a const. Okay, so that's a good learning point. Learning point number 3. Anytime something shouldn't change, make it const, and then that'll find, this will find bugs in your code if you do change it by accident, right? Like, if initial value is never supposed to change in here, like, sure, make it const. And then if you ever do something like, initial value equals 0 or something like that, we'll catch it. Like, because maybe you might make your own variable, like, x, like I had x before, and so maybe I might have int, and I can make another initial value, right? Or you know what I mean? Hey, here, perfectly valid code, right? And so if I have that here, that's perfectly valid C++ somehow. But if I have it here, then it won't compile because this initial value is that one. But if I put it here, then it's that one. Don't write code like this. This is bad. This is not what we consider good coding practice. But you can have multiple variables with the same name as long as they're not in the same scope. That is legal C++. So, yeah. This is called shadowing a variable, and it's bad. Like, don't write code like this. Okay. So with the const here, it'll catch it. All right. Write code with everything const by default. Then if I find I need to change something, remove the const. Yes. And so this is the const all the things mindset. Const all the things. And this is something that's become very popular in the computer science community. I kind of like 80% agree with it. I kind of 80% agree with it. In Rust, you have to like specifically like make a variable not const. Everything's const by default in Rust, unless you say that you can mutate it. So you put a mute in front of a variable to say that you can actually change it. In Rust, everything is constant by default. And the reason for that is because there's actually a lot of benefits to having everything be constant. You can prove things about your code that you maybe can't otherwise. Like here, I can prove that points per TD is always going to be 4. If it's not const, right, I can't guarantee, like, you got all these function calls and things like that. I can't guarantee that this will still be 4 down here, right? If it's not a, we got millions of lines of code in between. Can I guarantee that this guy's still going to be 4? Maybe, maybe not, probably not. But if you make it const, then you can know that this value is going to be 4. And then the compiler will just erase the variable and just say team score plus equals 4. And it won't use this variable at all. It's not a good name. It's a variable. It doesn't vary. It doesn't change. It's constant. Constant variables are a weird name. Constant variable. Is it a constant or is it a variable? Which one is it? I don't know. All right. And so I'll talk more about that sort of optimization benefit in a second, but I'm going to show you one more use of const, and that is learning point number 4. It's called constant pointers. So const pointers prevent changing the thing that they are pointing to. Okay. So if we've got team score 1, team score 2, I can make a pointer that is pointing at team 1's score. Okay. So we talked a little bit about pointers. We're going to go more into pointers on the next semester. I hope all of you guys signed back up for CSI 41. But pointers can be used to alter variables indirectly through the pointer. Or if you're Arthur Dwyer, they are called putters. Okay. I don't know why he calls them putters, but there you go. So if I take the putter here, I can say putter equals 420. And see out team 1 score. Okay, so what is team 1's score going to be? So I've got a variable called team 1 score. It's initialized to 0. I make a pointer that is pointing at it, and then I alter the value of it through the pointer to set it to 420, and then I print out the score. So what number is going to get printed out here? Is it going to print out 0, or is it going to print out 420? Put your votes in now. You got a 50-50 shot if you're going to guess. So I want everybody in chat right now to either say 0 or 420, because it's not, spoiler, it's not going to be anything else. Putters. Got 8 votes for 0, 2 votes for 420. It's going to print putters. It's going to print the memory address of it. I think that's almost everybody. Okay. Your votes are in. Let's see who's right. 420. Boom. Why? Well, because putter. Sorry. I can't help but laugh when he pronounces it that way. So putter here is pointing at this variable. It contains the memory address of this variable. And so when you use the star operator is the dereference operator. And so when you dereference it, it is as if I had typed here team 1 score. These two lines of code are exactly the same. Why? Because PTR pointer is pointing at team 1 score. And so if you dereference it, that star there, it actually gives you the original variable. Whatever variable it's pointing at, it's as if I had typed their team 1 score. So these two lines of code are doing the exact same thing. So I have adjusted the value of team 1 score through an indirect putter. Yeah. So what if I did this? Constant pointer equals reference team 1 score. You notice there's a compile bug now. What is the compile bug, do you think? I'm using a const pointer now. Team 1 score is not a const, right? I can still change the value of the score here. That's not throwing an error. But it's not letting me do it here. It says read-only variable is not assignable. What does that mean? What's going on there? Could I do this? Would this work? See out star pointer. It is a read-only variable. That is correct. So here, am I reading from it or am I writing to it? What do you think? When I'm couting it, when the highlighted line, not the line below it, the highlighted line. Am I reading from it or am I writing to it? I'm reading from it, so it's okay. Remember, const things, you can read from them, but you can't write to them after they're set. So what's going on is I can certainly output the value here. This is going to output 0, right? Because team 1's score here is 0. I cannot change it through the pointer, though. I can still change it here, but it is now a read-only pointer. So I could read the values there. I cannot write the values through the pointer. Okay. So that is a const pointer. Now, final thing is learning point number 5. 5 is 35. Number 5 is the optimizer. Is a thing. Okay. And const is its only profit. No, const helps it. Thank you. Okay. Caps lock and vim commands don't work well together. Okay, so what's the benefit of doing that? Well, what if you're passing off a pointer to somebody and you want to make sure they can't change your stuff, right? You pass them a const pointer. So like if there's a function call and the function's going to run through your array or something like that, oftentimes you pass them a const pointer, then they can't mess with your array through the pointer. It's like const reference, it just prohibits somebody from changing things they're not supposed to change. Here, there's no point. Like this has absolutely no point whatsoever. You would not do code that way. But in CSI 40, you will see that a lot of times you don't have the original variable. All you have is the pointer. And so everything you do is going to be star pointer this, star pointer that. And you have to decide, do I want a regular pointer or do I want a const pointer, depending on whether or not I want to change the things that I'm looking at. So yeah, we use pointers oftentimes when you don't actually have the original variable. For example, when you do new, right? It's like if you say int pointer array equals new int square bracket 1,000. There is no original variable, right? This is just 1,000 integers in an array that have no name. There's no variable. All you have is the pointer. And so if you wanted to pass this to somebody, you can make a const int read only array equals array. And then this read only array pointer, you can only read from it. You could say like cout read only array square bracket 40. Right? You can read from it, but you can't write to it. Right? So it grants read access on an array, but not write access on an array. Does that make sense? And in your own code, it's not going to matter, right? Because you still got R, right? R, right? Like I can change it, right? I could just, I could do this, and it'll work, right? The whole point of having a const pointer is usually when you call somebody else's function. Like there's some math library that takes an array of integers. You pass it as a const pointer so that they can't edit your values. If that makes sense. It's a safety, So does it mean it won't go out of bounds? Oh, I wish. No, you can very happily read from well outside the boundaries. Right? You can't write to it, but you can read from it. Right? So if you do that, it'll probably segfault maybe. Yeah, got segfault there. If you just go a little ways out of ways, though, it worked. It read from it. But if you go too far out of bounds, then you'll definitely segfault. Right? Reading still doesn't help, right? Because what happens is you try reading from out of bounds, and if you're too far out of bounds, then you are going to leave the segment that you're within, and the CPU's memory management unit will go you don't have access to that, and it throws a exception at you or something resembling an exception, and then it kills your program. So yeah, it doesn't help with segfaults. So okay. All right. So optimizers. So the optimizer was sort of the learning point for Bank of Keith. Now a lot of people didn't do Bank of Keith, and I kind of get it. It was kind of a meaty assignment. I don't think it was hard, but there was a lot of work to it. Not a lot of work, but I originally tried calibrating it at about a difficulty of 4, and after I did it, I was like, nah, it's a difficulty of 7 maybe. just because there's like 6 different menu options you have to implement, and you have to kind of understand maps and like accessing things through a map and the pairs and that kind of stuff. And so it worked out to be like a little bit harder than I thought, which is why I did the extra credit with Python. So, okay, so but the last thing on Bank of Keith. So let's G++. Let's just compile our code with and the backslash in front of G++ means no aliases, right? Because I always have G++ alias to do all these kinds of different things, right? So with a backslash, that means there's no alias. It is just running G++ by itself, no configuration flags at all set. So we're going to compile main.cc, and we need to compile it with std equals C++ 20. There we go. By default, G++ I think defaults to 17. So you need to give it 20 for it to compile. Okay. So if I try running the input tester, my code, I failed. My own code, the professor's own code, failed. Test number 9. Now, test number 9, for those of you that did the assignment, test number 9 is 200,000 lines of code, or not code, but 200,000 lines of input. Okay? And so the reason why it's slow is because it's processing 200,000 lines of input and then handling the bank transactions. Each one of these things is a bank transaction. I wrote a program that would randomly generate account numbers and would transfer money between them and stuff like that. Okay. So, so I had a lot of students who got 1 through 8 fairly easily, but then came to me and they're like, Gondor calls for aid. How do I pass test case 9? Because my code's correct. It just needs more time to pass. And your input tester kills my program after 3 seconds. So how do I pass it? And I said, what have you done? First of all, what have you done to improve the speed of your code? And they're like, well, we used hash tables, like you said. All right, that's cool. That's what you should be doing. Have you turned the optimizer on? And they're like, what's the optimizer? I'm like, now is a teachable moment. So if you want your code to go faster, and I've had students say they're going to tattoo this on their biceps before. If you want your code to go faster, the very first thing you should do is turn on the optimizer. So -03 is, that means turn on the optimizer at level 3. Is there a level 1 and a level 2? There is, but level 3 is better. So is there anything faster than level 3? Is there a level 4? Yeah, sometimes. What about O-fast? Yeah, we don't need to worry about that. O3, there you go. That's all you need to know for now. You're in CSI 40, first semester. So you compile the code with the optimizer turned on. And we run the input tester again. And it passes. Okay, so time a.out, read in input file 9. So write the output into dev null, please. So it takes 1 second to run. It takes 1 second to run with the optimizer turned on. And if we recompile it with the optimizer turned off, it was 0. That's an O and a 0, not 2 O's. If we run it again with the optimizer turned off, then it takes 2.2 seconds. Okay, so the optimizer did something, who knows what, that made it run over twice as fast. Okay. And there are other optimization levels. We can compile with 01, and I'm guessing we'll probably get most of the way there with 01. Yeah, there we go. Yeah. So even just 01 is enough to make it run over twice as fast, because there's not like anything really crazy in this assignment. 02, yeah. 03. Yeah, so 01 is enough for this assignment, but usually -03, that each one of those optimization levels turns on additional optimizations. And so what does that look like? Like, what do you mean by optimization? How does it magically make your code run faster? Well, let me show you. So I'm going to show you the, am I done here? Maybe not. If not, I can open it back up again. So there is a website called Godbolt. And Godbolt won't make sense to you really, like fully, it won't make sense to you until you take CSI 45. But yesterday in CSI 26, I showed it to my students, and they're like, "Oh, I was afraid of assembly before, and I'm not afraid now." I'm like, cool. Now you guys, are going to have your first exposure to assembly programming. Here. So what Compiler Explorer is, you write your C++ code on the left-hand side here. And then on the right-hand side, RMGC truck. Let's just start off something simple. And so what you have on the left-hand side here, why are we getting all this stuff? Getting extra nonsense here. None of that matters. Okay. So, all right. So what we have here is the C++ is on the left-hand side, and we've got the assembly that it generates on the right-hand side. Okay. And our code right now is pretty basic. It just returns 42. That's the error code, right? And you can see over here that the assembly generated is doing some stuff. It's pushing something onto the stack. It's adding 0 to the stack pointer and saving that into the frame pointer. It moves 42 into R3, moves R3 into R0. It moves the frame pointer into the stack pointer, and then it pops the frame pointer back off. And so let's focus on these two lines right here. Okay. So what move does, move is the assembly equivalent of saying x is equal to y. So what it's doing is that it's putting, and it goes this way. It goes to the left. So it's putting the value of 42 into register 3. Register 3 is like the hardware equivalent of a variable. And then it moves the value of register 3 into register 0. So why didn't it just put a 0 there? Right? Like, why move it from 42 into R3 and then move it from R3 into R0? Why not just move 42 into R0? Right? Do you guys see that? Like this is what you get when you don't have the optimizer turned on. When you do not have the optimizer turned on, you get absolutely terrible assembly code generated. It generates code that is absolutely garbage in quality. Okay? So if I were to do some variables up in here, like let's say integer x is equal to 10, and integer y is equal to 20, and z is equal to x plus y, return z, then integer z, sorry. Then you can see, I don't know why it's making this thing. Okay, so you can see here, we got these things, and we're subtracting 20 from it. So that, this is the stack allocation. Like, we've talked before about stack allocation and heap allocation. that right there is making room on the stack for X, Y, and Z. So X, Y, and Z are 4 bytes each, therefore it makes 20 bytes of stack space. Okay. So you can mouse over these things here, right? And it will actually show you what line of C++ it corresponds to. So you can see right here, we're putting 10 into R3. Okay. R3, like I said, these registers, they're like the hardware equivalent of a variable, right? So like if I was writing this code, I would put 10 into register 0 and 20 into register 1 and 30 into register 2 after we add them together and stuff. But if you look at the assembly that's coming out here, it puts 10 into register 3 and then it writes it to RAM. And then it puts 20 into register 3 and writes that to RAM in a different place. This is a pointer, basically. And then it loads from RAM, and it loads from RAM into R2. That's X, that's Y. It adds X plus Y together, and it saves it into register 3, which then gets written to RAM. And then it loads back from RAM into register 3. And if you're going like, but wait, that doesn't do anything, you would be right. This is a completely pointless line of assembly. Do you guys see this? Like, this is all the commands in assembly. This is the destination register. That's the one that gets written to. So we add X plus Y, and we save it into Z. And then we're writing Z into RAM. And then we're immediately turning around and reading the value from RAM back into Z. Right? I told you, if you don't have the optimizer on, you will get absolutely garbage performance. Absolutely garbage. Do you guys see this? Like, I know you don't know assembly. I'm well aware this is 4th semester computer science, but do you guys see why this is bad assembly? Like, you could just, like, not do either of those, actually, right? Because right now, it's going to copy R3 into R0. So we didn't need to do either of these memory accesses, right? Like, they're completely pointless. And so when you turn on the optimizer's like, that's pointless, and it deletes it. Okay? So the optimizer will take basically this here as input, and that's better. Okay, that looks better. Okay, so it adds X, Y, and Z, then it saves Z to RAM, then it loads RAM back into Z. So these could just be deleted entirely. And that's what the optimizer does. The optimizer will look at these things, be like, yeah, that doesn't do anything, and it cuts it. Okay, then it moves R3 into R0. So all of this could be deleted, and this R3 could just be R0, right? There's absolutely no point to have this instruction here as well. And in ARM, basically all of these commands take one cycle to execute with the exception of loads and stores. So if you have a computer that runs at 1 gigahertz, let's say, then it could do 1 billion adds per second, assuming it's running at full tilt, right? A load or a store are actually quite slow. A store takes probably about 4 cycles to execute, and a load can take up to 100. But if it's cache, because we just did the store, that's also about 4 cycles. So if we deleted this, this, and this, like before, these 4 commands would take 1 plus 4 plus 4 plus 1. So take 10 cycles. We could eliminate these 3 and just have this write into R0 instead of R3, and we would take 1 cycle instead of 10. And that's what the optimizer does for you. The optimizer will go through and be like, yeah, we don't need to do any of that, you know? And then it adds 0 to the frame pointer and stores it into the stack pointer and loads from the stack pointer plus 4 and puts that into the frame pointer and then returns. So you can see here the total running time cost of this whole thing is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's see. 13, 17, 21, 22, 26, 30, 31, 32, 36. Has a little bit of a cost, but let's say 37. So it'll take 37 cycles. In other words, the clock on your CPU goes high, it goes low, it goes high, it goes low 37 times. Remember, your CPUs run at like 3 gigahertz, 5 gigahertz, something like that. So the clock goes high, the clock goes low 5 billion times per second. So this isn't going to take long, no matter what. Like, it's not, you're not going to like break the bank, right? But what if you were doing this code 1,000 times a second, 1,000,000 times a second? Now all of a sudden, the optimizer matters. So let's just turn on the optimizer at the lowest level. You guys understand what it's doing? A lot simpler, isn't it? It's just doing the math beforehand. Exactly. When you have constant values, and 10 and 20 here, these are called constant literals, or integer literals. When you have constant values, the compiler can know what the result's going to be. Okay? So 10 is a constant, 20 is a constant. Z is being set to the sum of two constant values. So Z has a constant value of 30. And then we're returning Z. So the compiler just does the math, and it's like, yeah, the answer is 30, dude. And it just returns 30. Like, there's absolutely no reason when you run your code for it to actually do any arithmetic at all. No point. There's no point whatsoever for your code actually adding 10 and 20 every time. So what happens, and this is on the lowest optimization setting, what happens is the compiler's like, that's a constant. Okay, I know what it is. Now, if we were to, for example, do a CN, right, then we can no longer know CN double right arrow X. Yes, it's include stream. Right. So now it can't optimize it away, right? So the it's going to load here, and that's branches to there, and then it loads into the return. Okay. Somewhere within here, it's going to add 20 there. Okay. So this line of code here, so R0 is the return value. So that is the value returned by CN, basically. And it saves it into RAM. And then we're adding 20 to the return value and saving that into X, essentially. Or saving that into Z, basically. And that's what the optimizer runs. So you can see this whole thing here is like 24 lines of code. If we have no optimizer turned on, then you can see it's substantially larger, right? There's substantially more lines of code, and it's far less optimized. It's writing to RAM, loading the same value back from RAM. Right here, it's storing R3 into RAM, and then it's loading from a different place into R3, and then it's loading this value that was just written there. It's loading that into R2. And so this whole thing could have been switched to just move R3 into R2, but instead it goes to RAM each time, which is 4 cycles when it doesn't need to be. And then it finally does the arithmetic. So if you turn on the optimizer, your code will be much faster just by default, because by default, the assembly produced by your compiler is garbage. It is absolutely terrible code. And the reason why it is that way, it's because it's safe, right? It will generate code that is guaranteed to work, and it relies upon the fact that the optimizer will delete the stuff that are redundant. The optimizer will just go be like, yeah, that doesn't do anything. Kill it. Okay. So what if so basically we can't hard code everything now, right? Because we have to read from the user, right? So after we read from the user, we add 20 to the result, and then bail out. Okay. So so that's the difference between a const and not a const, right? So if we go back to how it was before, then Yeah, it puts 30 and quits. So, yeah, I don't know why it's trying all these weird things over here. Okay, anyway. So, yeah, so when you have constants, you can get more performance a lot of the time. Now, let's go back onto the server. Is that kind of interesting to you guys? Are you guys scared of 45 now, or more interested in 45 now? You could technically take 45 after 41 if you want, but I recommend 41. There's only the good news is in assembly, like you can learn all of ARM32 assembly in about 2 weeks. There's only like 15 or 16 assembly commands that actually matter. There's hundreds of them, but like most of them are just variants of each other. Like there's subtract, and then there's reverse subtract, and there's move, and there's move not that flips all the bits when you move them. There's and or, and compare, and add, subtract, and multiply, and branch. And there's only about 15 or 16 actual assembly commands that actually matter to anybody. Okay, so okay. So one thing I do want to show you is something called constexpr. My absolute value and x return if x is less than 0, we are going to return negative x. Otherwise, we're going to return positive x. And this is constexpr. Okay. So if we see out, let's just return mabs negative 10. And run it. There's no cout statement, right? So where did that negative 10 go? Well, it's right here. It's 10. So that's the error code. Remember how I told you guys what you return from main is the error code? Whenever you run the program, it doesn't appear to do anything, but actually that error code is being set. So the error code is 100. Why? Because it's the absolute value of negative 100. So this constexpr thing here, constexpr means it has to be compile time determinable. And has to be, it depends on what context of constexpr it is. So what does that mean? Okay. So const int x equals read is okay, right? So if we write this code, it's not compile time determinable. So it's actually going to have to do a little math. Echo there. But if we make x constexpr, that means that x has to have its value determined at compile time. And so it's more const than const. Const, remember, just means it gets set once and then can't be changed. Constexpr on a variable means it has to be determinable at compile time what value it has. And you can't know what value it's going to have because you don't know what the user is going to type. So if you did this with like negative 100, it's fine. Okay. And so if we compile our code, g++-03 main.cc, run it, get the value of 100, g++-S main.cc. You can see that the entire function called doesn't exist. Those two highlighted lines are the entire program. Everything else is just, not important. Okay. That's the program that's being generated. Notice there's no function call. There's no comparison. There's no, if it's less than 0, multiply it by -1. Otherwise, no, none of that. The reason why this works is because everything is constexpr. And so there's been this major push in C++ in recent years to have like constexpr functions, constexpr if statements, You could, for example, say if const expr x is less than 0, return 42, else, let's do this. If x is greater than 0, return 42, otherwise return the mabs of x. This code will never run when you run your program, because it's constexpr. Constexpr means that the compiler figures out which one of these two things is true. Is it true that x is greater than 100? It is? Okay, then it returns 42. You will not see an actual if statement in the code. It's pretty cool. It will actually just literally delete the if statement. The if statement will not appear in there anywhere because the compiler can figure it out. So if we look at this code in assembly, once again, delete 1G, delete Shift G, you can see that main is literally just returning 100. It doesn't do any of the if statements or anything like that. And that's why there's been such a push in C++ to do more and more constexpr stuff. Now, if I were to set x equal to 100, then look at the source code, you'll see that it is now returning 42 instead. No if statement anywhere within there, right? The compiler itself figures out the if statements, and oftentimes it can figure out for loops, main.cc. So you can do something like this: int sum equals 0, for int I equals 0, I is less than 100, I plus plus, sum plus equals I. So we're going to sum up all the numbers from, let's say, from 1 to 100. Okay? And then return sum. Actually, let's just make it 1 to 4. Let's just make it simple. So I know what the answer is. It's 10. Right? So we're going to add up the numbers from 1 to 4 and return it. Okay? So do you guys think you're going to see a for loop within there? Or can it figure out what this number is going to be? We've got function calls, we've got if statements, we've got a variable that can't vary, we've got a for loop. Is it going to actually run any code at all, or is it just going to return a value? What do you think? Is there going to be more assembly in there other than just like return 10? Yeah, basically. What do you guys think? And so if constexpr only works with constant expressions, right? So if this was not constexpr, it won't work. It would work, I think, if it's just const. Yeah. Because this is a constant expression over here. So regular constant actually work there. But yeah, if you take that out, it won't compile. Okay, so let's take a look and edit the source. And look at that. And once again, all of that code that we had in there, the optimizer's like, the answer is 10. There's no if statement to be seen. There's not a for loop to be seen. There's no variables to be seen. There's no reader writes to RAM. There's no sum that's being summed together. None of that exists. What does it do? It returns 10. Done. Okay. Cool. Right? And so if you were to benchmark this, right, like in the previous class, we're out of time now, but in the previous class, I benchmarked, adding up a billion numbers, and it took like 3 seconds, right? And then I turned the assembler on, the optimizer on, and it was like 0.01, like just negligible time. Here's the answer. I've pre-computed it for you. So even though there's an int, yeah, even though there is an int, it doesn't exist. For all intents and purposes, if you have a constant, it probably will get deleted from existence because it doesn't need to actually read and write it to RAM, because we know what the value is. The value is always 100. The value is always 100. And so every time you see an x down here, return, x plus sum, let's say. It could do arithmetic, but why would it? Because the compiler knows what the answer is. The sum of all the numbers from 1 to 4 is 10. X is 100. 100 plus 10 is 110. The compiler can do math, right? The optimizer can do math. And so if you look at the assembly that comes out of this, it's just going to return 110, right? Isn't that cool? So there's a variable, but the variable doesn't exist. It's called constant value propagation. Like it'll actually, there's something called constant value propagation. So usually const variables get deleted from existence. Like they probably won't show up in the assembly code because it knows what the answer is, right? Should be a little bit more specific here. Const variables get deleted from existence. Sometimes constants can have different variables. Like if you did a read or something, you could have a const actually exist. But for pretty much anything that's constexpr like this, they will not show up in the assembly. It will just get erased. Okay. So there's a website for benchmarking. Yeah, there's like Quick Bench and things like that where you can like put in different versions and stuff. Ray's got a time though today. So let's see if we can find it. Quick bench with quickbench.com. Okay, string creation, string copy, bench. Okay. So let's try this. So we're adding up all the numbers from 0 to 9999999. Let's see. There's some weirdness with this. I don't remember. Something. I could just run it on the server. Let's see here. Actually, yeah, okay. All right. So what's actually funny is that like if you don't use the variable at all, it'll actually delete it'll delete everything. It won't do any of it because like if you don't use the variable ever, like you don't print it, you don't return it, the optimizer will be like sum's not being used, and it won't do the for loop. It won't make it'll just delete all of it because that's all pointless code. And the optimizer is very good at figuring out what is pointless code. So you either have to see out something or return something, and then it won't get deleted from existence. But if you don't have either of these two lines here, then the optimizer will just delete that entire for loop and not do a billion additions. Okay. So, okay. So, plus -o0. So with the optimizer off, time a.out, it takes 3.3 seconds to do the math. If we time it with the optimizer on 01, then it takes 0.8 seconds. If we do optimization level 2, it takes 0.4 seconds. And if we do optimization level 3, then it does 0.1 seconds. So you can see there is a pretty substantial difference in running time based on the optimization levels, and especially just like anytime you care about running time, don't have turn the optimizer on. You know what I mean? So yeah, you guys get that? Like, what's the big learning point for today? Compile your code with -03. That's the big learning point for today. Okay. And then the optimizer will do its magic, and your code will just run faster. Quite, like in this case, 30 times faster. Okay. So that's our class for today. So we learned 3 or 4 different meanings of const and constexpr, things like that, and talked a little bit about assembly. Just a little taste of it. I didn't really want to get into explaining the whole thing, but a little taste of assembly, and then the value of the optimizer, and just a couple of the tricks the optimizer does. There are a lot of tricks. The optimizers do. They're very brilliant. They're very well written. They're usually smarter than you. I can still handwrite assembly that beats the optimizer, but I have to work at it. Like it takes hours for me to kind of sit down and try different approaches in assembly and kind of hand tune something to beat the optimizer. The optimizer makes pretty good code real fast, real simple. You don't have to write assembly. You just write C++, and then the optimizer will come in and just generate for you some pretty good assembly. Not the best, like I said. I can still beat it when I try. Like if I really care about running time, like I was able to get a Raspberry Pi encode 4K video at like 30 frames a second or something. So, like if you try, like you can beat it, but it's pretty good. Good. Join the constexpr cult. Yeah, const all the things. Okay. Any questions from today, guys? I'm gonna be able to answer questions on const on the quiz for today. Does Java have an optimizer? Yeah, absolutely. But you're not going to need the optimizer for rainfall. Rainfall is not a very resource-heavy computation. Java's actually got some really interesting things, because Java has a runtime environment that reads the assembly, the Java assembly, the Java, opcodes or whatever they're called. And it can actually generate actual assembly for your CPU if it feels like it. It's called JITting, just-in-time compilation. So it'll actually translate the Java assembly into real assembly wherever it determines there's hot loops. Like if the heart of your program is this one for loop, then it will take the time to rewrite. It's all automatic. You don't even know about this as the end user or the developer, but the Java virtual machine will oftentimes take Java assembly and translate them into real assembly, and then save that, and then use that instead of the Java instructions, and it speeds it up immensely. Sometimes you can find the Java code actually faster than C++ code. Not often, but I've seen it on benchmarks where this one benchmark will run faster in Java, and that's because their optimizer has essentially pulled out all of the Java and just made an assembly program that's highly optimized. And for whatever reason, their optimizer was able to see through the code better and put together a better solution than the C++ version. So it doesn't happen that often, but it can happen that Java could actually be faster than C++. What slows the speed? Bytecodes? Yeah, because normally what happens is the Java virtual machine reads a Java assembly instruction because oh, we're doing a comparison. And then it has to tell the CPU, do a comparison. And then it looks at the next thing. Oh, we're adding 5 to a number. Okay, CPU, add 5 to a number. And it has to sit there and translate the Java assembly into actual assembly. But after it's done that, it can save the translations and JIT them, especially when it's something that gets called a lot. So there's a lot of research on optimizers and that kind of stuff. And at the end of the day, it actually does result in Java not being too terrible. Yeah. So, all right, guys, that's it for today. And remember, we have a end of the year party next Friday That'll be in person, AC1 114, kind of morning to afternoon time. We're going to have a LAN party. We're going to have some food. We're going to have some Smash Bros. There's no final in this class, so you don't need to worry about that. After you get Java Rainfall done, you're done for the class. You can take off, go home, you know. But we do have an end of the year party not this Friday, next Friday in AC1 114. I'm going to be in person at the pit tomorrow, 6 to 8 p.m. to help you guys with Java Rainfall. So if you're on campus, 6 to 8 p.m., a student asks me AM, and I'm like, no, not AM. Definitely not. 6 to 8 p.m. tomorrow, I'm going to be in the pit helping students with Java Rainfall because it's due on Friday. Jack Sims is going to be giving, I think, a talk. He just texted me. I don't know. Okay. But we'll probably have a last extra credit workshop on Friday, and I'm looking at putting together a meditation workshop for finals week. I need to talk to some of my friends that wanted to come to it and see when they're available, and I'll survey the people that went to the meditation workshops before and see if you guys are interested in one last extra credit meditation workshop before the end of the year. So if you are, let me know. Send me a message or something, and then I'll make an announcement about that. Okay. That's it for today, guys. Thanks a lot. Peace.